Right, so if we have a beam, now what we have, we've definitely got a pinned reaction there. That's we can represent by A. We've got a roller joint at B. So there's only a reaction in the vertical direction. This 6 kilonewton is not a reaction, it's a force pushing up. So this beam can move up or down. In terms of reactions, they're fixed at these 2 points, but at this 6 kilonewtons, that can move upwards and down. And the steps that we would take is that we'd look at our reactions, then our shear force, the bending moment, and then we've got our curvature. So let's look at the reactions. So if we're taking moments around A to try and find what the reaction is at B, so sum of moments around A equals 0. We'll say that everything going around anti-clockwise is going to be positive. So I've got my finger on point A, so I'm ignoring this force at A because it's passing through that point. So use my moments as force times distance. I've got my 6 kilonewtons times by 10. So I'm putting my distances in the brackets. And I've got B times by 4. Then I've got my UDL. Now, in terms of force times distance, my UDL is 1.5 times by this distance 6. So that's my force. So 1.5 times by 6 meters. And then the distance to the midpoint, where it acts as 4 plus 3, so it's acting here. So I'm be multiplying all of that by 7. All of that equals 0. B, we find, is 0.75 kilonewtons. Because it's positive, we know for definite that this reaction is pointing upwards. Now we have got, when you look at this this load setup, we have got a UDL that's coming down, so that's 1.5 times by 6, so that's 9 coming down and 6 going up. Now, it may have been possible that this force here could have been pushing this load up to such an extent that B might have had to have been pulling down. So if that was minus, it means that the arrow would be pointing downwards, but what we're finding is that there's not much load on B, but it's definitely holding up the UDL. And then we'll do sum of forces, vertical, saying upwards is positive. So we've got A, B, we've got the plus the C, which is the 6. Then coming down, we've got 1.5 times by 6 meters. All of that equals 0. We know B is 0.75, so we can find out that A is 2.25 kilonewtons. It's positive, so we've guessed the direction correctly. So that's the answers for our reactions. Then we draw our shear force diagram. So just directly below, I'm going to draw my shear force, and that will be in kilonewtons. So my beam is representative of 0 kilonewtons. So this A here is 2.25, we got 0.75 0.75 at B. So as I slowly reveal the forces at the top here, I go up 2.25 and I stay at 2.25 until I reach my next force. So I go up 0.75, so I've got 2.25, then I'm going up 0.75 to 3, and then I've got my UDL, and my UDL is 1.5 kilonewtons per meter. So every 1.5, every 1 meter, I'm coming down 1.5, and what you'll find is that you end up with a linear diagonal line going down to -6. So this line here again, every meter down 1.5. That's the UDL. And then I go all the way down to -6. And then by the time we've reached the end, we're going back up 6. And if we come back up to 0, then everybody's happy. So where our shear force passes 0, what's that? Yeah, maximum bending moment. So it's good to find out where this location is that it crosses 0. So if we call that distance x, so that's from B to the point where it crosses 0. So if we added up all of the forces as we're travelling along the beam, we have 2.25 plus 0.75, and then coming downwards we've got this 1.5 kilonewtons per meter, and x meters will at the distance x long will come to a shear force of 0. And we can rearrange that so that we end up with this x equals 2 meters. Say again? Why is the x come from B? Because what we're trying to find out is that so much of this 1.5 brings us to a point 0. Because the UDL started at B. If the UDL started at A, we could look at the distance from there. But because we're starting from the position B with the UDL, X amount of the 1.5. So where we have the shear force, next we can move to the bending moment, which will be in kilonewton meters. So again, I'll draw a line to represent 0 kilonewton meters. And if I cover over the beam again, so if I was to take a moment around this point, I've got 0. So I've got your moment is force times distance. If I've got 2.25 times by 0, so I'm starting at point A is 0. So at A, bending moment equals 0. And then if I move along the beam, so 1 metre times by 2.25. So I'll be moving to 2.25, 2 times 2.25, and then all the way along until I reach this point B, which is 4 metres. So at B, the bending moment, force times by distance, 2.25 times by the 4. That gives me 9. And that would be a linear, straight line going up to 9. Then as we're going along the beam with the UDL, we've got our distance to this 2.25, you've got this distance here to the 0.75, and then you've got so much of the UDL coming down. And I won't do this for each sort of metre along, so you can sort of draw the shape. We know that it's going to be a curve, a parabola, because that's the shape for a bending moment for a UDL. What we'll do, we'll just do the bending moment at the shear force passing 0. So at the bending moment max, so that distance is 4 plus 2, so it's, which is 6 metres from A. We'll have 6. We'll say that everything going around anti-clockwise is going to be positive. So if we're at this point here, we'd have 6 times by the 2.25. We'd have 2 metres times by the 0.75. And there's 2 metres of the UDL coming downwards. So you've got minus 2 times the UDL, and that acts halfway. So it's 2 times by 2 again, divided by 2. That equals 12 kilonewton meters. So it'll end up curving, reaching a maximum at this point, and then dropping down to 0. So it will be a value of 12 there. So that's linear, and that's a curve, that zone there. So in terms of the beam itself, the bending moment doesn't pass 0. So if we have a line that represents the beam, which way does the beam bend in terms of the curvature? Again, with the bending moment, when you look in books, they say put the bending moment on the side of the tension side. I'm not bothered whether you had it drawn like that or whether you'd had it drawn like that underneath, like a mirror. I'm indifferent which side that you have. It's the main values to me that is important. But which way will it curve? Because when it passes 0, then we move from a hog to a sag. So we've got this, we've got a point load going up. We've got this UDL that's pointing downwards. And then another force. So is it going to bend that way? But if it was going to bend that way, then surely this force, because that's like we've got 9 coming down and we've got 6 coming up, like surely this 6 should create a little bit of a curve upwards. I would suggest for the curvature that what we have is that the force, the curvature is like this. So the force of the 6 is pushing upwards, and we have a smiley face from A all the way through to C. If we were going this way, we'd have like a sad face that would be going from A all the way around to almost C, but this 6 would be creating a bit of an upwards curve, and if that was the case, then you would have to be crossing 0 with the bending moment. Because we don't, we need to have a curve which is either like that, or a sad face, or a smiley face, and that's the deflection shape that we are looking for.